Mathematics is our best attempt to understand the reality that we live in using logic and reasoning. So the best place to start with this class is to define a few ways of reasoning, namely the important ones, inductive and deductive reasoning. And then we'll move into pattern analysis and sequences maybe in a few videos, but we're going to start with inductive reasoning. Then the next video will be deductive reasoning. Then we'll move into pattern analysis and sequences. So we have a quote here by an author who I forgot to write. This is an Albert Einstein quote. It says, "As far as the laws of mathematics refer to reality, they are not certain. And as far as they are certain, they do not refer to reality." So our laws of mathematics are not always as certain as we believe them to be. In fact, we now know that there's a lot of probability in mathematics, a lot of uncertainty, but we just try our best to make sense of things. And the easiest way to start making sense of things is using a few reasoning tactics. So we'll start with inductive reasoning. Our definition is inductive reasoning is the process of arriving at a general conclusion based on observations of specific examples, meaning that we generalize what's going to happen by the fact that it's happened a certain number of times a certain way in the past. So, for example, and I left this example here from last semester because I thought it would be funny to include, or from last year, because we are clearly online, but the example that I had on this is, if I leave home at 2 p.m. every afternoon to get to Rutgers in time to teach this class, then I can conclude, after a certain number of cases, after a certain number of times that it worked out, that if I leave home at 2 p.m. next week, I will get to Rutgers in time to teach this class. And that is my inductive reasoning. I take a base case, I say this is something that's happened before, it's happened often, so I can say it'll probably happen again the next time. So our question becomes, is inductive reasoning always foolproof? We'll look at a few examples and we'll make that decision ourselves. So our first example, kind of our first counterexample, is the 10 symbols that we use to write numbers, namely 0 through 9, are called digits. In each example shown below, the sum of two two-digit numbers, gives us a 3-digit number. Can we conclude that the sum of any two two-digit numbers results in a 3-digit number? And it doesn't require a lot of effort to find out that we cannot make that conclusion. We cannot definitively say that the sum of any 2-digit numbers is a 3-digit number. In fact, we can think of an easy counterexample just by going a little smaller, maybe doing 30 plus 25, which we know is not going to be a 3-digit number, it's just going to be 55. So these reasoning tactics, while they do work in a general case, they do have counterexamples, they're not always perfect. But we can use inductive reasoning to find patterns, to figure out patterns in things. So we'll use inductive reasoning to find a pattern in the lists of numbers here, and then we'll find the next number in the sequence. And we do that by looking at the numbers next to each other. To get from 3 to 12, what do we do? Well, one thing we could do is we could add 9. We know we could add 9, but we also know another thing. We could be multiplying. We could be not adding. There's a whole host of things we could be doing, but we could add 9, or we could multiply by, 3 times what is 12? 3 times 4 is 12. Well, which one's happening? Let's move on to the next case. What do we do with 12 to 21? What happens? Do we multiply by 4? Well, we don't, because multiplying 12 by 4 will give us something higher than 40, and this is a 21. So what's happening here is we are adding 9. And then we continue. We check each case to make sure that that's what's happening. Here, that's clearly what's happening. And here, that's clearly what's happening. So to find the next number, we just follow the pattern again. We added 9, added 9, added 9, so let's add another 9. And 39 plus 9 is going to be 48. And I see I have a typo here, 1, 2, 3, 3. But take a minute, pause the video, and find the solution to the rest of these on your own. Now from here to here, I see I have that same plus 9 or times 4. But from here to here, I see that I'm multiplying by 4. So I see that I'm multiplying by 4 here to here. I might take a calculator or some thinking, but from here to here, the same thing happens. So to get my next number, 768 times 4 is 3072. And they're actually pretty easy tricks to multiply by 4 that we'll talk about in the live version of our class. Some patterns are a little harder to realize. Some patterns are a little harder to see. If you paused the video and did what I said, with this next one, you might run into some trouble. Because to get from 3 to 4, you can really only add 1. But then to get from 4 to 6, you're certainly not adding 1. But you're not multiplying by the same thing to get from 3 to 4 and then to get from 4 to 6 either. So what is happening here? Well, let's just talk about what's happening. First case, we're adding 1. Then we're adding 2. From 6 to 9, we're adding 3, and you immediately see that's what's happening. Then the next case, we're adding 4 plus 5, which means in our last case, we should add 6, and 18 plus 6 is 24. Now, if you truly did not pause the video to try them, please pause the video to try this one and see if you can find a pattern. In this case, I see that I can multiply by 2. 3 times 2 is 6. But then from 6 to 18, I need to multiply by 3. 6 times 3 is 18. But what's 18 times 4? 18 times 4 isn't 36. So I'm multiplying by 2 here. Then I'm multiplying by 3. But 18 times 2 is 36. So then I'm multiplying by 2 again. And then 108 is 36 times 3. And we see that we just have a little bit of an alternating pattern. So we're multiplying by 2 here. So we'll have to multiply by 3 in the next case, and 216 times 3 is 648. I assume when you're watching these videos, you are taking notes as we go, and you can pause the video wherever if you have a question or something you want to think about. Please pause the video during piles of examples so that you can complete the examples. Let's continue. This next one is a specific sequence. A sequence is a list of terms that are related to each other by a rule. So in this case, we look for the rule, and this rule is a little harder to find. If you didn't scroll ahead in the video, take a minute and try to figure out what this sequence could be. What is happening here? So the pattern in this case is actually, we have the first two numbers, we have a 1 and a 1, and then to get the next number, what we're doing is we're adding the previous two together. 1 plus 1 equals 2. 1 plus 2 equals 3. 2 plus 3 equals 5. It's hard to denote how this is happening. 3 plus 5 is equal to 8. 5 plus 8 is equal to 13, and so on and so forth. So our next number here is just going to be 13 plus 21, which is 34. And this is a sequence that shows up often in nature. It shows up all over the place. So this is going to be the end of our inductive reasoning video, and I'm going to post the Fibonacci sequence video next. So please watch this video next. So there was one more example that I wanted to do for the last video, which is just this example, which is nice and cool because it doesn't include numbers. It's not just all about numbers. We can use inductive reasoning once again to follow through with this example. So what is happening here? We have a 1 dot here, we have 2 here, we have 3 here, and it's in a circle. We see that we're going from circle to diamond to circle to diamond. So if I'm looking for the next one in this sequence, and take a minute and try to find the next one on your own, well, the first thing that should jump out at you is the next one in this sequence is going to be a circle with an X in it, because we go circle, diamond, so the next one is going to be circle. And then we need to know where the dots go. Well, there's a 1 dot here in the right side, then there's 1 dot on the top, then there's 1 dot on the left, then there's 1 dot on the bottom, so the 1 dot is just circling counterclockwise. So we're back at the right side again for the 1 dot. What about the 2's? The 2's are circling counterclockwise as well. The 2 is always to the left right here. So this will be our next 2. And this will be where the 3 dots are. Nice and simple. And that is our last example, besides this cool little article. And then after this, we will move on to deductive reasoning.